So it is lecture number 15 and we will talk about simple univariate linear model. That means the hypothesis function we are taking linear in sense, and generally you can go for nonlinear approach, but that would be a little bit difficult. First we need to understand a lot about linear model, then we will go to see another little bit more than linear, that we are calling it generalized linear model. Also we will cover those things in later part. So first I will discuss this. So coming to outline, and if I talk about the origin of derivation of such kind of linear model, it is basically based on conditional expectation. So conditional expectation in probability class, we might have already uh, aware of that. Uh, what what kind of thing? What is the characterization or property of conditional random variable? That means suppose we are having two random variable x and y, and just I am asking one condition that we suppose we observing y first. So in that case we can define, if you are observing y first, then you can define a random variable for each observed value of y. That would be a conditional random variable, and it will have a conditional probability mass function. Suppose x and y both happen to be discrete random variable, and we know that data generally happens to be in discrete in fashion, so mostly we will discuss about discrete approach. Okay, so definitely if it is a random variable where we apply conditioning, that means we observe y first, it means the x given y, it will have a probability mass function, and that probability mass function we are calling it conditional probability mass function. Okay, now anyone can say that if you define conditional expectation with respect to this observed value of y, then what is the nature of this one? What would be this? Definitely, yes. What is the definition of expectation? Suppose x is a discrete random variable, then you are finding expectation of x. So here it is in conditioned by y. So we have to multiply x with the corresponding conditional probability mass function x given y of x in order to calculate the expectation. If you understand this, then that means the starting page of linear model you understand very well. So this we are calling it conditional expectation for each y. Now tell me, after calculating this one, whether this conditional expectation would be function of y or not? Anyone? If you are calculating this expectation, then whether this would be, after calculation of this expectation, we definitely put conditioning by y, so whether it would be function of y or not? Okay, you can look back to probability lecture for that. Definitely I would like to say that it would be function of that observed value y. So likewise you are able to, you are putting conditioning over y, and hence so you are observing all value of y. So we know that here each value, for each observed value of y, we see that the conditional expectation is a function of y, and hence we can introduce a new uh, random variable that would be expectation in term of conditional expectation x given y. So it is a function of the second random variable y that we have already observed. So and we know that function of a random variable is again a random variable. So conditional expectation is a random variable. It is a random variable. So if you're talking about conditional expectation, so everywhere in linear model we will try to find conditional expectation as a function of whatever thing whatever we are observing as a function of that random variable. If suppose someone is observing x first, in that case you will get conditional expectation of y given x, and that would be function of x. So this scenario. So if you are going for a simple regression problem, then generally we, what we say, we try to say that our response y happens to be what? Some function of our input variable x, some function of input variable x, that a small letter, and we don't know about this f. So one such app is given by this regression. This we generally call it a regression function or regression equation. So this expectation of conditional, that means conditional expectation of response given what we call it input variable. That is the one approach, one idea of linear model, but it is very difficult to calculate, find this one, very difficult. So what we are doing, we try to give some kind of model structure. One of the model structure is linear model. Suppose x and y both are actually coming from normal distribution, then by default this conditional expectation will take the linear form. You can express it as alpha plus beta times x linear if x and y both are coming from normal distribution. That means joint distribution of x and y is a normal distribution. Then easily you will see that the conditional expectation of y given x, it would be alpha plus beta time x. It would be linear function of x. But suppose it is not always possible that your data set always will be generated from some normal distribution. It may come from any kind of distribution. That time it is very difficult to get a linear structure form of this one, but definitely we will set up a linear form of this conditional expectation in order to estimate this function f. So those things we will discuss in detail here in this lecture. So it is all about overall main crux of what we call it linear model. So coming to outline of this lecture, first I will talk about a simple univariate linear model, or you can call it univariate simple regression also you can call it. So regression is a very general, a specific word, and what we call it univariate linear model or univariate. Right now I'm not putting linearity assumption, so univariate model. So we are not putting, it may be linear, it may be non-linear. So first we will discuss about this one. Okay, after that I will talk in detail about one specific case of this model, that when we take linearity pattern, that means by default you assume that your data set is coming from some kind of normal distribution. That time directly you will get exact linear model, but in general it is not always possible that data is coming from some normal distribution. It may come from uh, something else. Okay, so that time we will go for some kind of approximation, or approximation we will provide it through estimation. So those things we'll discuss here. So coming to first part of this lecture, that simple univariate model or regression model. Here I'm not putting linear word here. Remember that a linear word is not coming, so it is a very generic derivation of the model. So what we do, so you can go for maximal likelihood estimation here, but I will talk, simplest one is the least square estimation. How we can talk about this? So consider uh, we are having two random variables, x and y. X is we are taking in sense of response or output variable, and y in sense of attribute or input variable. And we consider that y is statistically related to the attribute x. So we try to find uh, statistical dependence of y on x. That means whose value have already here, value of x has been already observed. That means we know that what kind of value x is taking. That means that is the data set. We know that, and we want to see the dependency of y over x. So it is here simple word is related with that we are taking a single random variable, single attribute. Single attribute, that's where simple word is coming. Now if you talk about univariate, again here we are taking a single response, so that's why we are calling it univariate. Single response or single output variable is meant for univariate, and simple meant for single attribute. Here y is single response, or you can call it out. Response is a very common name, so that's why I'm using response. Many way you can use response. And here simple is coming with respect to single attribute. So here I would like to write it single attribute or input. Attribute input both are same. Attribute is a common word. Attribute. So every word is having meaning. I told that. And here I am not using linear word till now. Now, so then we will go for the least square, or you can call it minimum or least, both are same. Least or minimum. Least mean square estimation of y is given by the following conditional expectation. It is coming. That means here we are observing attribute x. Based on that, we try to estimate the response variable y. So how we will estimate, because x we have already observed, that means we know what is the distribution of f. So common name of distribution we will denote it by f of x. It might be x. If x is a continuous random variable, then it would be PDF. If f is a discrete random variable, then this would be what, probability mass function, that you know. So it would have a distribution. Simply I am calling it like this way. X we have already observed, that means we know about what is f of x. We know, we are having that idea. Now based on that, we don't know f of y. We don't know, so we want to know the distribution, but directly this one is very difficult to calculate. So in place of calculating that distribution of y, what we will calculate, uh, there is a dependency of y on x, so we can calculate conditional distribution of y given x. So sometime notation I will take notation p. Don't confuse with notation p. P is also same distribution function. So I can take in place of f, I can replace it by p as well. The next notation I have taken p. So here situation is coming like this one. We are going to calculate conditional expectation of y for given observed value of x. Okay, so that means how we can find expectation. So expectation, we know that suppose we are here, we assume that y is a discrete random variable, then we are using just summation. So summation over y into corresponding conditional probability mass function of y given x. Conditional probability mass function of y given x. Why? Because x we have already observed, that's why we are saying given. Given and observed, condition or given, both are the same meaning. Now if you try to, so what we do, it is uh, we will do little bit calculation, or in such a way, what we know that from the multiplication rule, a joint probability of x and y can be calculated as a multiplication of which one you observe first. So here x you are observing first, so first density of probability mass function of x will come, then we need, after x we try to calculate probability mass function of y. That means we approach here conditioning thing. So conditional probability of y given x of y, this is the joint probability mass function. That's why I have expressed this. So if you, what you do, if you bring this probability mass function of x left hand side, then you will see that the conditional probability mass function of y given x, it is the ratio of this joint probability divided by marginal probability of x. It is directly coming from here. Okay, from the multiplication rule through which we have defined joint probability mass function. So here in this process we can say that among the all, so y, our target is, we want to estimate y. Our target always want to estimate y. So best estimate which will give, so we try to estimate y as a function of x. As a function of x we try to estimate y as a function. Right now I am putting approximation as a function of x. So among these several estimator, which one would be the best estimator? So best estimator, it would be given by this conditional expectation y given a. How it is coming? So that we can replace it, we can see it here. So just let us consider mean a square. This one expectation is mean, so mean a uh, mean a square error. So what is g of x is one kind of estimate of y, simply you can say that estimate of y. So you are doing uh, this one is the error, then you are squaring it and you are finding mean. So full name of this one is mean square error. And g of x is any kind of any estimate, we don't know that that may be least square estimate or that may be any other estimate. So it is a very general kind of estimate of y, and that's why error we try to find the mean of that square of error. So if you try to do little bit manipulation here, that means adding this term, that conditional expectation of y given x, and subtracting, then it will give the same equation, there is no issue. But what we do, we bifurcate, decompose this one into two terms. Easily it can be decomposed into those these two terms. So during efficiency I had already discussed this one. Consider right now this one is one kind of estimator. So it is just there, for the notation of estimator I had taken theta cap. So consider this conditional expectation is having similar feature what theta cap had. Okay, similar feature it had. But so that what is this what is this, you can observe that uh, this quantity has been, now this mean square error has been decomposed into two terms, this one and this one. Okay, and both are what, dealing with a square term, so both are always non-negative. and and hence we can say that as this quantity is sum of these two, so by default we can say that this quantity plus this equal the some positive thing is equal to this one, and hence we can say that this quantity would be always less than equal to mean square error. So this quantity is always less than equal to mean square error. That means if you take a estimate as a conditional expectation, and with respect to that what error you will get, that would be the least error, that would be the least error with respect to any arbitrary estimate. You can observe that here. So this one is with respect to any arbitrary estimate g, and this would be always greater than equal to if you take mean square error with respect to what we call it this conditional expectation. That means uh, mean of or expectation of a square of y minus expectation conditional expectation is y given x. Y given x whole square. Okay, so you can always see that. So that's why we can say that this is the least square estimate of y among the all estimator g of x. As conditional expectation uh, y given expectation of y given x is the least square estimator of y. So that is the concept. From here this mean square measurement, you have already seen that. Now I will talk about, so once you did estimation of y, so y was what, it was some function of uh, the attribute x. So I am putting here approximation. So the best estimate we through least square approach we had taken expectation of y given x. This one is coming with respect to conditional expectation. So let us give a name to this. So it is one estimate, so we are calling it estimator. We generally denote it cap. So y cap we are calling it y cap. So this y cap is not exactly equal to y. So if it is not exactly equal to y, then there is an error. That error term we say that y minus y cap. this is the error, or we simply say that we predict through this way. So this error, you can also say that it is prediction error. That means we want to uh, predict y value for given x. So this one is a prediction error. Then what is the relation of this prediction error with our attribute x? So the prediction error is having orthogonal relation with respect to input variable x, input or attribute x. So orthogonality, that we will see it here, how it is very easy to establish orthogonality. So we will establish orthogonality. So orthogonality of prediction error, that means y minus 1 least, this always remember that now onward I will call it, this is what, least square estimate of y. Y will have several estimate, but we are just worrying about least square estimate, LSE. This one is the specific estimate, that one is the least square estimate or least square estimator. Okay, so with respect to this, we are defining prediction error y minus expectation of y given x, and we will see that this would be perpendicular to x. And hence, if you talk about in uh, statistical manner, so that perpendicular nature, it would be converted into uncorrelation. It is uncorrelated. That means if you try to find the correlation between this error term in x, then that correlation would be zero. That means not correlated, uncorrelated. So we will see here like this way. So in order to see the uh, this relation, this one is perpendicular to this, what we do, we will try to find expectation of product of x and y. And there is a story why we are finding it. So in order to find this one, we know that here what, it is a joint random variable. That means it is a x into y, that means it is one function of x and y. So we have to, in order to calculate the expectation of this one, we have to take joint probability mass function of x and y. So that's why this g of xy, here g of xy is what, x into y simply, or you can say that x into y, that through expected rule it is coming into the corresponding joint probability, because it is a function of two variables. That's why joint probability is coming, and we have to sum this over all value of x and y. Afterward, what we will do, we again apply multiplication rule to convert this one into sequential pattern. That means x we have already observed, so we will take benefit of that, and we will convert this one as a product of probability mass function of x time conditional probability mass function of y given x. Because this one would be given, it would be given from the problem, it is very much certain that it would be given what would be the distribution of attribute, that would be given to you, that would be known to you. And based on that, conditionally you can find distribution of y. Conditionally, directly you can't find the distribution of y, but conditionally you can find. This one is a feasible job, or it would be definitely hidden there in the problem, so you can calculate it. So if multiply these two, in total you will get your joint probability. Okay, so that's why I'm converting this joint probability into computable form. So this is the computable form, we want to say that. So afterward, what we do, like have you gone through change of order of integration in math 1? Anyone would like to comment over that? How we perform change of order integration? Suppose we are having a double integration, and uh, it is some function of x y. It is very much important. Change of order, we are going to integrate function of two variable, uh, which here areal element will come dx dy, and here it is coming like this one. Okay, sometimes it happens that here this one is the innermost integral element, outermost. So that means first this would definitely, it would be function of x and y, but here if dx is coming first, then we first need to integrate with respect to x, then after we are integrating with respect to y. That is the order of integration. But sometimes it is happening, what is happening here, that sometimes it is very easy to integrate with respect to y, easier than x. Integrating with respect to y is easier than x. So you have to apply, uh, there are many rule, but Faguni rule or another rule used to call it. So here you have to apply change of order of integration. Anyone have gone through that change of order integration? Can you? Yeah, that and just master it. It is very much essential. And if there is a very interesting kind of book that Thomas and Finney, you can get a very good theory over change of order integration. So you can apply it through that areal element that you need to know that domain. So you can always apply change of order of integration. Remember that that function must be continuous. Condition is that function must be continuous, and you can always change. So if you know, very fine, definitely you will find. So here it sorry, f of x y, here dy will come first, and dx whatever looks easy you can go with that. So this is change of order of integration. A similar concept is applied here, change of order of summation. Similar concept, you know that there is analogy between summation and uh, uh, what we call it, integration. So similar concept is applied here. We apply change of order of summation. First inner summation was with respect to y. Now in inner summation here you can observe that we can was with respect to uh, x. So we just do little bit, and we made inner summation with respect to y first, and after that what does it becomes? It is your conditional expectation. This is conditional expectation of y. So a conditional expectation of y is coming. This one is the conditional expectation of y, and further you are uh, summing x times conditional expectation of y times probability mass function of x. And x is already what it is, a observed value, and you have already, I already mentioned that this is conditional expectation of y given x. So what it would be, again a function of x, and that means x into g of x is again a function of x. And from expected rule, what we do when we find expected rule, that means if you are having a random variable, how you find expectation of that function of that random variable? We apply expected rule, g of x, that means function of x, time corresponding probability mass function of x. So same thing is coming here. So this total term is what, up to here it is function of x times probability mass function of x. So this is, we are calling it expected rule. In short, I will write it expected rule here. Okay, so from the expected rule, it is talking about expectation of the random variable x time g of this one, this expectation of y given x. So expected, through expected rule, you will say that this one is actually expectation of this quantity. What is this? This is what it is saying, that it is product of uh, random variable x and another random variable, that one is conditional probability uh, expectation, conditional expectation, this one. Okay, so here we are started with expectation of x into y, and we got the derivation that this one is equal to expectation of x time least square estimation of y. This is what, least square estimation of y, least. Okay, so we can say that if you just bring this left hand side, then we will see that expectation of x into y minus expectation of y given x, so it is equal to 0. It is equal to 0. So from here we can claim that x is orthogonal to, what is this, this one is the prediction error. So x is orthogonal to prediction error, or uncorrelated. In terms of statistics, we are saying x is uncorrelated with prediction error, and in terms of deterministic situation, we can say that x is perpendicular to this prediction error. So that is the derivation of orthogonality of prediction error with input variable or input attribute x. So the result is intuitively appealing, and for if the prediction error were correlated with x, then the information of x could not have been used efficiently in the forming the best estimator. It is very much intuitive from the here. So that's why we call it this conditional expectation estimate that is coming from the conditional expectation. We are calling it is the best estimator of y, because it is having zero prediction error, perpendicular to orthogonal prediction error with respect to an attribute. So orthogonality itself is optimized in linear algebra. You might have already seen that orthogonal. If you talk about projection, then orthogonal projection always giving optimized approximation. That one is itself optimized. That's why linear algebra is not doing calculus. Without even doing calculus in linear algebra, you are doing optimal thing. So whatever technique that one that derivation of linear regression you might have already seen in linear algebra, and we didn't apply their calculus technique, but we got that projection part as a optimal solution. Okay, now we will go to linear model. So we will take a specific form of that regression function, or simply we call this one as a regression function. Conditional expectation of y given x. That means we want to estimate y for given attribute x, and this we are calling it a regression function. Simply you can write this is function of x, some function of x. I may change the notation of this. Some it would be some function of x. So this we are calling it a regression function. It is the backbone of understanding linear model. So what kind of function you want to proceed, whether you are taking linear function or nonlinear function, depend upon that. It will decide the model structure and you will get the corresponding model. So here I will take a linear model. That means this would be a linear function of x, a linear function of parameter x, linear. I will take f as a linear function. That means parameter will decide the nature of linearity, not x. So if the suppose if the joint distribution of x and y, it is normal. Suppose x and y joint, if you try to find joint distribution uh, x f of x y, it is normal, then it is very much straightforward to find the expression for this regression function or conditional expectation. Common name is regression function, a specific name is conditional expectation. Why? Because it is uh, computed as a conditional expectation. So if you want to go for common name, then you can call it regression function. There is no issue. So if you try to find an expression, uh, if you get x and y from normal distribution, then this one is having an explicit form. That one is linear in nature. That would be like this way. It is linear function of x. This we call it what? Intercept. And this we are calling it slope. W1 is slope, W0 is intercept. It is all about that how we estimate this W0 and W1 for given data set. We want to estimate it. Right now, W0 and W1 both are unknown to us. So we have to estimate, and we see that linearity is defined with respect to this one. That's why a function is a linear function. So parameter is deciding the linearity here, not the random, not the input attribute or input variable. So it is defined. So this is a linear function. So if you x and y both are coming from normal distribution, then definitely it would be linear structure. But suppose x y not coming from linear, that normal distribution, then it will have some nonlinear pattern. Like if it is coming from suppose x and y both are coming from uniform distribution and some other distribution, then you will see that this function, this regression function, it would be no more linear. So that example I will talk probably in this class or next class. I will talk that if I taking distribution, this joint distribution from some other distribution, then things would be complicated. So here what is happening that uh, I told that if you are taking this linear representation, then you can call it is a linear model, or simply why? Because name of this one also sometimes calling it regression function, so you can call it regression equation as well, a regression model also you can call it. So here what is all about that in this simple univariate linear model, all about is that we have to estimate omega naught and omega 1. Sometimes I'm calling it w for making it weight, or sometimes that means weight it defined weight, and sometimes I'm calling it omega. There is no, so it is omega notation is written. Both are meaning for same. Omega is Greek word, w is English word. That is the difference only. Okay, so estimator of, we have to find estimator of omega naught and omega 1. It can be expressed in term of the first order and second order moment of joint probability, that joint distribution of x and y. Any question? Anyone is having any question? No. Okay, I will discuss further. So here I am talking about all about estimation of omega naught and omega 1. So I mentioned that these can be estimated in term of first order moment and second order moment. First order moment means expectation, and second order moment means definitely that one is not various, x square or something will come. This one is the first order moment and x square is the second order moment. Likewise, expectation of y would be first order moment and expectation of y square would be second order moment. By uh, engaging those together, or you definitely you can calculate various and other parameter also you can calculate with the help of those moment. That is to say, we wish to express omega naught and omega 1 in term of expectation, that of x, expectation of y, variance of x and variance of y, and also second or one another second order that structure y will we will get from this all these moment, that one is the covariance of x and y. If suppose there is some covariance between x and y, so that also, so all these five together will estimate omega naught and omega 1. So here I will take one example. After that, I will go to discuss further. So before going to talk about example, I will talk about estimation of omega naught and omega 1. So that general formula I will talk about. I will give a general formula. Last slide I told that these can be expressed in term of first order and second order moment. Then what are the explicit form? That derivation I will talk about. So in order to go for that, I will take the linearity of the linear model. It will be our primary assumption in order to derive the estimate of this one. So that means we are assuming that our regression function is linear in nature. That means expectation of response, conditional expectation of y given x, it is linear function of. Remember that here I am not saying here about joint distribution of x y. That may be anything. I don't know, but I am taking an assumption here that here this conditional expectation is, or regression function is linear, omega naught plus omega 1. So this structure I have taken, omega 1 times x1. So linear function we have taken. So consider a simple univariate linear model. This is the linear model as a linear function of x. Okay, now we it is as a linear function in term of parameter, the parameterized form. So now we apply expectation both side. If you apply expectation both side, what we will get? Can anyone can say that if you apply expectation, what you will get? What is the expectation of conditional expectation? Anyone? What is the expectation of conditional expectation y given x? What is your, what is value of this one? What would be this value? Anyone law? No, law of iterated expectation. Have you heard that? So from the law of iterated expectation, expectation of conditional expectation y given x, it would be equal to expectation of y. You can watch those probability lecture again in order to see the derivation. I have already discussed all this, and link is already given there in reference as well, so you can watch all this derivation. Derivation is very simple again. So here we have taken the regression function as a linear function. Okay, linear function. Now from here we can calculate expectation of y by using this one. So we will calculate by applying expectation operator both side. So if you are applying operation expectation operator both side of this linear function, then from law of iterated expectation it will be converted into expectation of y. And here this omega naught, it is what? It is a constant number. So expectation of a single number happens to be what? With expectation we are taking with respect to here the random variable x and y, that would be, that will come. So expectation, so what would do, it is independent of that, so that was just omega naught will be the, here expectation of omega naught is again omega naught with respect to x and y variable. And expectation of here x will be expectation of x. Omega naught is behaving like constant with respect to x, and there is no dependency of omega naught over x, because these are parameters, these are defining function, it is not defining what we call it, it is not much related with random variable, these are defining function. So functional approach we are calling it. So from here we can get expectation, one explicit form of expectation of y equal to omega naught plus omega 1 times expectation of x, and from here we can say that omega naught equal to expectation of y minus omega 1 time expectation of x. Okay, now using this further, what we do, substitute this omega naught here in the definition of this linear model. So it will, what it will take the, it will be converted into single parametric form. So there is only one single parameter omega 1 only, because omega naught we have already expressed like this way. So we are our intention is we have to estimate omega naught and omega 1. So that's why we are doing all these. So that's why this linear model becomes like this way. It involves single parameter omega 1. We will try to find one explicit form of omega 1. How we can find? So now we do multiplication, uh, uh, both side multiply with x, and we are taking expectation here. After coming to here, we do multiply x both side, and we are taking, after that we are taking expectation. That means expectation of x into conditional expectation of y given x, that means regression function. It would be again here, we had already seen that what would be this expectation. This expectation would be equal to expectation of x into y. That derivation I talked about in previous slide. So it would be equal to this one. And if you see in right hand side of this one, I'm talking about, I'm applying this one here in this linear equation. I first multiply with x, and after that we apply operation of expectation here in this, call it equation 1, over this equation 1. So due to that it will convert right hand, this left hand part, it will be converted into expectation of x into y, and in right hand part it would be omega naught time x, and we are finding expectation of this. That's where this term is coming, and x we are multiplying here both sides, so x become here this x square, so expectation of x square. So it is directly coming from here. Next we will do one more thing. What we do, uh, we are multiplying in the same what here in this equation, we had already seen this equation, call it equation 2. This is equation 2. In equation 2 both side we multiply with expectation of x. Here we do multiply with expectation of x. Okay, so after that we will get this kind of equation. Okay, so we are having one equation, this one, so call it equation 3rd, and this one is the equation 4th. So using equation 3rd and 4th, what common thing we can see, that uh, using this and this we can define a very interesting concept that we are calling it covariance. So that's way, what is the definition of covariance between x and y? It is talking about the difference between uh, expectation of x and y and product of corresponding expectation. This is the definition of covariance. You can get it here. There is a very interesting relation. If you try to derive this expectation of x directly, you can come to derive the expectation of x. It would be what, sum of covariance plus product of expectation, or you simply you go to proceed with the definition of covariance. From there you will get this derivation. So I am taking the definition of that derivation of covariance in term of this term, and we have already calculated here expectation of x y equal to what, omega naught into expectation of x plus omega 1 into expectation of x square. And here second term, this one, product of expectation of x and y, we have calculated it like this way, omega naught times expectation of x plus omega 1 times a square of expectation of x. So we are substituting this value here in the definition of covariance, and after that substitution we will see that omega naught time expectation of x and omega naught time expectation of x both are common, so both will cancel out and only we will have the term containing omega 1. So omega 1 into expectation of x square minus a square of expectation of x. And what is this? This is actually definition of the variance of x. From the definition of variance of x, you might have already seen that. And hence we see that covariance of xy is equal to omega 1 times variance of x. So from here we can derive, because x and y are given to us, x and y are given to us, so that's why this one is the data set given to us. So we can estimate, one estimate we got it as the ratio of covariance of xy with variance of xy. This one is the one estimate of omega 1. Now similarly, if you are able to get estimate of omega 1, substitute back it here in this equation, equation 2. In this equation 2, the what you will get estimate of omega 0 easily from substitute back. You can call it equation 5. Use equation 2 and 5. So give a, I'm giving name like 2 like this way, one easy to find. So using 2 and 5 you can get the estimate of omega 0 in term of covariance and expectation and variance. In term of this one you can estimate this one also. You have already estimated omega 1. Okay, so this is the estimation process for linear model. Remember that the structure regression function I have taken a linear function. It is omega 0 plus omega 1. If it is non-linear, then process would be different.